Hello all, welcome to the Interpretability tutorial session. In this tutorial, we will look on how to perform code interventions with the Codebook features library. Codebook features are method used in training and interpreting neural networks. They help make these models more understandable and controllable by incorporating discrete learned codebook entries into the model's layers. So, in each layer of a neural network, Codebook features introduce a bottleneck where continuous activations are converted into discrete codes. Like the continuous activations be set of random vectors 0.1, 0.2 something, and those will be converted to a discrete value, some 18, 19 or something like that. So, this process is also called as vector quantization. The network learns a set of fixed vectors which we call here as codebook entries. Instead of using the raw continuous activations, the model uses these discrete codes to represent the data in each layer. Okay, so during the training, the model learns which codes from the codebook are best suited for the various tasks, and this helps the network to focus on specific patterns or features in the data. The loss function of the model is given like this, where always is the existing loss function of the neural network. It can be anything. So, we add the main part of the loss function is this, where C out represents the output of codebook at layer I, okay, where C I in represents the input to the codebook at layer I. SD is a short form notation of stop gradient. It means that during back propagation, gradients won't flow through this part. And we are taking L2 norm over this Euclidean distance between Ci out and Ci in. So, for example, if we take the word cat and we are doing in the layer 3. So, the summation represents from 1 to n layers. Okay, let's take that it is in the layer 3 now. During the forward pass, input to the layer 3 would be some n-dimensional vector which represents the word cat. The network finds the closest matching vector in the codebook. So, we have a codebook and it finds the closest matching vector in the codebook, and the output of the layer 3 will be the closest codebook vector which might represent cat or some similar word. Okay. Purpose is minimize this loss, which means making the codebook output of cat as close as possible to the input representation of the cat. Okay. That's how this loss function works. If you see this example, this is directly taken from the paper. You have a topic video game, and the corresponding code of this topic is 18. Okay, the original generation is the given prompt is the war was fought, and this is the original generation. On two fronts, the war was initiated in 1914. Blah blah blah. Okay, but we want this. Whenever we give this prompt, not only this prompt, any prompt, we want the topic to be steered towards the topic video game. So, we give video game topic, we give the code 18, and we want the, whenever we give any prompt, we want the model to generate and steer towards this particular topic. So, if you see, the steer generation is the war was fought on both sides and was only the second game to deal with one of the battle follow in SimCity to the Blade 2 or something. Okay, it is something related to the video game. Okay, if you see football also, the same prompt is given. If you see this and this prompts are same, but it is steered towards football. It says that in its first 40 years, in the summer of 1946, the Cardinals of All American Football Conference were rapidly, something like this. Okay, it generated some output regarding the topic football. Okay, so in this tutorial also we will see how to use these codes, and we give some topics and we steer the discussion towards certain topics. Okay. First, it starts by importing the codebook features. If it is not installed, it will install the codebook features, this particular code. Okay. Once you install the packages, restart the session. Otherwise, there will be some errors later. here we turn off automatic differentiation in PyTorch. So this is done to save GPU memory, since we are only interested in model inference, like generating the text rather than the training the model. So also disabling gradient computation reduces the memory usage and computation overhead. Okay, we take the tiny storage 1 layer 21 million parameter model as the original model, and authors have codebook model in their GitHub repository. We consider that model and we store it in the pretrained path. Okay, we set the device to CUDA or else CPU, whatever it is, whatever the particular notebook is having. If you want to connect to GPU in Colab, you can go to the view resources, change runtime type and select T4 GPU here. So you can avail 15 GB of GPU every time you use. Okay. So now we have two models: the original tiny storage 1 layer 21 million model and the codebook model. Okay. Now we will use the existing function that authors proposed, which is wrap codebook, and we wrap these two models in original codebook model. Okay. Now we set this original codebook model to eval, and so that we say that there is no training required and we want to evaluate the model, like we want to generate the text of the model. Okay. From that model we create a hooked model. So we keep everything as same. If you see, everything is set here to false. So center unbed, if it is set to true, it normalizes the embeddings to have mean of 0. Okay. If fold value biases is set to true, it simplifies the model by merging the biases. But we are taking exact same model, we are taking the exact original CB model and just replicating it into the hooked model. Okay. Now we call it as CB model. We convert the original CB model, we use this function convert to hooked model, and we store it in the label CB model. Okay. Now we also set the CB model to the eval, and the tokenizer is the existing tokenizer. Okay. Now we will see if there is any difference between the hooked model and the original model. Okay. So we pass a sentence. This is a random sentence to test, and we convert this sentence into the input tensor using the tokenizer, and we set the input tensor to the device. We check the output from the original CB model. Original CB model is the primary model. Before it is not the hooked model, and we also have the hooked output from the CB model. Okay. Original CB model is the original CB model, and CB model is the hooked model. Okay. Now we will see if the distributions between these two outputs are different. So I said this function sees if there is any difference between the distribution between these two outputs. So the tolerance level here is set to 10 power minus 4. So if it is if there is a difference, it returns false. If there is no difference, it returns true, something like that. Okay. So here the decisions are same. So the output of both original CB model and CB model are same. So we have everything same. So here comes the interesting part of this tutorial. Authors have found the codes of particular topics at a particular layer and with attention head 13, with some attention head. So the topic dragon occurs at layer 0 with the attention head 13 with the code 4670 17640. Okay. So all these codes, like we have seen previously in the example, movie is 18, movie is 12, football games is 18, video games is 18, something like that. The code for dragon here it is 4670. You can also see the different type of codes that are available in this particular link, and it's an interesting graphic user interface where you can go see for which word where the code is occurring and at which layer the code changes and all. Okay. So first we use a blank one, and this is for default generations, like there is no steering here, but we define all the codes and the codes for the corresponding topic. Okay. For the dragon, these are the particular codes, and for slide these are the particular codes, and so on and so forth. For baby it is all these are the codes. Okay. So this function this converts the strings to the list of topic codes of the type code info. Okay, because code info is what the library uses. Our topic is baby now. We pass the text input once upon a time to the model, and we are asking the model to say start its input, start it output using the phrases once upon a time. Okay, we pass the same text into the CB model, we convert the text input into the tokens, and we append it to the CB model, and we are asking the same input to be repeated for the 10 times. Okay. Then we use generate with quotes function to generate the outputs starting from once upon a time and steer towards the topic baby. Okay. Now in the output you can see there are different type of stories that are generated by the model. So here once upon a time there was this, the baby was so excited and all. Once upon a time there was huge fist, it was so big. The baby was so proud of himself and all. So it is kind of steered towards generating something related to the topic baby, no matter what. Okay, this is how the steering looks. But yeah, quantifying this method is bit tricky. We have generated few stories, we have seen baby word is occurring everywhere. Okay, that's good, we are able to steer the topic towards baby, but how to quantitatively evaluate, how to get a metric, how to show that yes, this particular quotes work for each and every iteration or something like that. Also, if we can't search for baby, we can't search for simple regex pattern in baby and say that yeah, these many times this occurred and these many times it didn't occur, something like that, because the word may be babies and we are searching for the topic baby. There will be a huge difference there. Okay. So to do the same thing, what we do is that we generate prompts with different starting sentences. Once upon a time, once there was, a long time ago. Okay, these are the different set of prompts we are asking the model to start with. Okay, and we generate all the prompts using all the given codes that we have mentioned previously and ask it to stay towards that particular topic. So we do it for all the topics using all the codes using all these three particular prompts. Okay, this particular function generates codes for all the prompts and all the topics and all the codes, and it stores in prompt completions set. Okay, now we have prompts, now we have outputs for all the topics stored in the prompt completion set. Now what we do is that we calculate two things here, topic in prompt completion and topic in prompt completion average. So this is something like calculating TF and IDF, where you see whether the baby has occurred in the 10 instances. We are asking the model to generate 10 different stories, and we see if baby has occurred in the 10 different instances in that particular iteration. And we also see how many times baby occurred in all the generations. Like though the topic is baby, we also see is baby generated while we are asking it to steer towards dragon, while we are asking to steer towards flowers or something. So it's something like TF-IDF. We check in the individual thing and also across all the things. So this represents the same thing, topic in prompt completion and topic in prompt completion average, which will give us a broader idea that yeah, this particular sentence is stayed in the only topic that we are asking, and it is not stayed in other topics, something like that. Okay. This is for the original CB model. We generate all this for the original CB model. In the same way, we also generate for the from the original model. Okay, we also give the same prompt and ask it to generate a story. We see if baby has occurred. First, here we know that we are steering towards baby and we have sentences towards baby, but here we don't steer anything. We are just asking the model to generate sentences on that particular one. I give input once upon a time and we ask the model to generate sentences based on that particular thing, and we see if the topic, if there is any topic occurring, if the baby topic has occurred in that particular 10 iterations or not. Same like what we are doing in the previous stayed generations. Okay, we print the all the outputs that we have generated. If you see baseline, when there is no topic steering, dragon has never occurred in the generation. Slide has occurred 7.5% of the total generation. Friend has occurred 45%. Flower has occurred 15% and baby has occurred only 2.5%. Now we have given the topic dragon, we are asking it to steer towards dragon. So 77.5% has dragon, so it is stayed. You can see the differences where in the baseline there is 0. The dragon, the topic never had this particular topic dragon, but when we are asking to generate on dragon with the codes, with all the codes that authors have proposed, the average steering is 77.5%. So in the same way, the baby has 97.5% steering in that particular generated output. So this is how we can change the individual codes. We can use the internal codes to the way that we want the model to generate sentences, in a way to have the model generate the sentences that we require.